Preparing for a software engineer at Skyroot Aerospace interview. You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Why do you want to work as a software engineer at Skyroot Aerospace? I'm interested in Skyroot because software here directly affects launch readiness, vehicle reliability, and mission success. That is very different from building a generic application. I like environments where code must be efficient, tested deeply, and written with real hardware constraints in mind. My background in systems programming, debugging, and automation fits well with avionics, simulation, telemetry, and ground software. I'd bring disciplined engineering and a strong ownership mindset to mission-critical work. While answering, focus on your motivation for space technology, Skyroot's launch vehicle mission, willingness to work in high-reliability systems, and how your software skills fit aerospace constraints. Question 2. Walk me through a software project you built and explain the architecture. I'd explain the project from the problem outward. For example, in a telemetry dashboard, I separated ingestion, processing, storage, and visualization, so each layer could scale independently. The backend consumed data streams, validated packets, stored time series values, and exposed APIs to the front end. I owned the data validation and alerting logic, wrote unit tests around edge cases, and improved latency by batching writes. The key lesson was designing clean boundaries before optimizing code. Make sure to cover the problem statement, architecture choices, modules, data flow, technology stack, trade-offs, testing approach, and what you personally owned, rather than only describing the team output. Question 3. How would you design software to receive and process real-time telemetry from a launch vehicle? Real-time telemetry software must treat data integrity as the first priority. I'd design an ingestion layer that validates packet structure, checksum, timestamp, and source ID before forwarding data. A buffering layer would handle burst traffic, while critical parameters would trigger threshold-based alerts immediately. I'd store raw packets for replay and processed values for dashboards. If packets arrive out of order or are missing, I'd flag quality status rather than silently filling values. In your answer, talk about packet ingestion, validation, timestamping, buffering, ordering, loss handling, alert generation, storage, visualization, and how you would prioritize reliability over cosmetic features. Question 4. What is the difference between a process and a thread, and where would you use each? A process is an independent execution unit with its own memory space, while threads run inside a process and share memory. I'd use processes when isolation matters, such as separating a control service from a visualization service. I'd use threads when tasks need fast communication, like reading telemetry, while another thread processes alerts. Threads are lighter, but shared memory creates race conditions, so locks, queues, or lock-free structures must be used carefully. Be sure to mention memory isolation, context switching, shared address space, synchronization risks, performance implications, and practical examples such as telemetry processing, simulation workers, or UI responsiveness. Question 5. Explain how you would debug an intermittent software failure during hardware-in-the-loop testing. For intermittent failures, I'd first avoid guessing and capture evidence. I'd enable structured logs with timestamps, input values, state transitions, and hardware interface responses. Then I'd compare failing and passing runs to isolate patterns like timing, sensor noise, packet drops, or resource exhaustion. If possible, I'd replay captured inputs in a simulation. Once I have a hypothesis, I'd change one variable at a time and document the root cause clearly. While answering, focus on reproducibility, logs, timestamps, input capture, environment differences, instrumentation, hypothesis testing, rollback strategy, and collaboration with hardware, avionics, and test teams. Question 6. How do you handle race conditions in multithreaded code? Race conditions happen when multiple threads access shared state, and the result depends on timing. My first preference is to reduce shared mutable state using message queues or immutable data. When sharing is necessary, I use mutexes, atomics, or read-write locks based on access patterns. I also define lock ordering to avoid deadlocks. In critical systems, I'd add stress tests, thread sanitizers, and code reviews because race bugs often don't appear consistently. Make sure to cover shared mutable state, critical sections, mutexes, atomic operations, message queues, deadlock avoidance, testing limitations, and why deterministic design is important in aerospace software. Question 7. What data structures would you use for a telemetry alerting system, and why? I'd combine data structures based on the access pattern. A queue or ring buffer would handle incoming telemetry in order while bounding memory usage. A hashmap would store parameter configurations like thresholds, units, and severity. For alert prioritization, a heap or priority queue could surface critical events first. For trend checks, I'd maintain a sliding window per parameter. The goal is predictable latency and controlled memory, not just theoretical efficiency. In your answer, talk about queues for streaming, hash maps for parameter lookup, heaps for priority alerts, ring buffers for recent history, and trade-offs around memory and latency. Question 8. How would you find a memory leak in a C or C++ application? I'd start by confirming the leak through memory usage over time under a repeatable workload. Then I'd use tools like Valgrind, Address Sanitizer, or heap profilers to identify allocation paths that are not freed. In C++, I'd review ownership rules and replace raw owning pointers with smart pointers where appropriate. I'd also check containers, callbacks, and error paths. In long-running ground or test software, even small leaks can become operational issues. Be sure to mention symptoms, heap growth, ownership analysis, smart pointers, Valgrind or sanitizers, profiling, code review, and how leaks can become mission risk in long-running systems. Question 9. What is your approach to writing reliable code for mission-critical systems? For mission-critical systems, I prioritize clarity, predictability, and verification. I avoid clever code that only one person can understand. I define assumptions explicitly, validate inputs, handle errors deliberately, and log enough context for debugging. I write unit tests for logic, integration tests for interfaces, and use static analysis where possible. I also think about failure modes early. What happens if data is late, corrupt, missing, or outside expected limits? While answering, focus on defensive programming, clear requirements, simple design, code reviews, unit and integration tests, failure modes, logging, static analysis, and maintainability over cleverness. Question 10. Explain the difference between TCP and UDP. Which would you use for telemetry? TCP provides reliable, ordered delivery using acknowledgements and retransmissions, but that can add latency. UDP is lightweight and faster, but packets can be lost or arrive out of order. For real-time telemetry display, UDP may be acceptable if each packet has timestamps, sequence numbers, and quality flags. For file transfer or configuration updates, TCP is safer. In aerospace systems, the protocol choice depends on whether freshness or completeness matters more. Make sure to cover reliability, ordering, latency, retransmission, packet loss, bandwidth, real-time constraints, and why the choice may differ between onboard systems, ground systems, and post-test analysis. Question 11. How would you test software that interfaces with sensors or avionics hardware? I'd use layered testing. At the unit level, I'd mock sensor inputs and test parsing, validation, and error handling. At the integration level, I'd use simulators that generate realistic data, including noise and boundary values. For final confidence, I'd run hardware-in-the-loop tests with actual devices and timing constraints. I'd also inject faults such as disconnected sensors, invalid packets, and delayed responses. That helps verify both normal behavior and graceful degradation. In your answer, talk about mocks, simulators, hardware-in-the-loop testing, boundary cases, calibration data, fault injection, timing validation, regression tests, and coordination with electronics or avionics teams. Question 12. Describe how you would optimize a slow algorithm in a production system. I'd first measure before changing anything. Profiling tells whether the issue is CPU, memory, I/O, database access, or algorithmic complexity. Once I identify the bottleneck, I'd look for better data structures, reduce repeated computation, batch operations, or cache-safe results. I'd keep the change minimal and compare before and after metrics. Most importantly, I'd run regression tests, because a faster incorrect system is worse than a slower correct one. Be sure to mention measuring first: profiling, identifying bottlenecks, complexity analysis, caching, batching, data structure selection, avoiding premature optimization, and verifying correctness after performance changes. Question 13. How do you ensure code quality when working under tight launch or test deadlines? Under tight deadlines, I'd be more disciplined, not less. I'd prioritize the riskiest and most mission-impacting code paths for testing and review. I'd keep changes small, use checklists, run automated tests, and make rollback plans clear. If a shortcut is unavoidable, I'd document the risk and create a follow-up task. In launch-related work, speed matters, but uncontrolled changes can cost far more time during integration or test campaigns. While answering, focus on prioritization, risk-based testing, code review discipline, automation, feature flags, rollback plans, clear communication, and avoiding shortcuts that create hidden operational risk. Question 14. What is the difference between stack and heap memory? Stack memory is automatically managed and tied to function calls, so local variables are allocated and released quickly. Heap memory is dynamically allocated and lives until explicitly freed or managed by ownership mechanisms. Stack is faster but limited. Heap is flexible but can leak or fragment. In embedded or aerospace software, memory behavior matters because unpredictable allocation patterns can affect reliability, latency, and long-duration stability. Make sure to cover allocation style, lifetime, speed, size limits, ownership, fragmentation, recursion risks, dynamic objects, and why memory awareness matters in embedded or performance-sensitive software. Question 15. How would you design a logging system for launch test software? A good logging system should help engineers reconstruct what happened without overwhelming the system. I'd use structured logs with timestamps, severity, module name, event type, and correlation IDs. Critical events should be flushed reliably, while high-volume debug logs can be buffered or sampled. I'd separate raw telemetry from application logs but link them by time. Log rotation and retention policies are important because test campaigns can generate huge data volumes. In your answer, talk about structured logs, severity levels, timestamps, correlation IDs, performance overhead, log rotation, raw data retention, searchability, and usefulness during post-test root cause analysis. Question 16. Explain object-oriented programming concepts with an example relevant to aerospace software. Object-oriented programming organizes code around objects that bundle data and behavior. For example, different sensors can implement a common interface like read, validate, and calibrate. The rest of the system can process sensor data without knowing whether it came from pressure, temperature, or inertial hardware. Encapsulation protects internal details, abstraction simplifies usage, and polymorphism makes extensions cleaner. I'd still avoid over-engineering. Composition is often safer than deep inheritance. Be sure to mention encapsulation, abstraction, inheritance or composition, polymorphism, maintainability, and a practical example such as sensor interfaces, actuator commands, or telemetry processors. Question 17. How would you handle missing or corrupt telemetry packets during a live test? I'd never silently treat missing or corrupt data as valid. Each packet should have checksums, sequence numbers, and timestamps so software can detect corruption, gaps, and out-of-order delivery. The display should show data quality flags and alert operators if critical parameters are affected. For calculations, I'd use safe handling rules, such as holding the last value only when explicitly allowed. Raw packets should be retained for replay and post-test analysis. While answering, focus on detection through sequence numbers and checksums, data quality flags alerting, safe defaults, avoiding false precision, replay capability, and communication to operators. Question 18. What is continuous integration? And how would you use it in an aerospace software team? Continuous integration means merging code frequently and automatically validating it through builds and tests. In an aerospace team, I'd configure CI to run unit tests, static analysis, formatting checks, and selected integration tests on every pull request. For critical branches, I'd require approvals and traceable build artifacts. CI doesn't replace hardware testing, but it catches basic failures early and prevents broken code from reaching expensive integration environments. Make sure to cover automated builds, unit tests, static analysis, integration tests, version control discipline, artifact traceability, deployment gates, and why CI reduces late-stage integration surprises. Question 19. How would you solve a coding problem where you need to detect duplicate packet IDs in a stream? If packet IDs arrive in a stream, I'd use a hash set to detect duplicates in average 01 time. But for an unbounded stream, I wouldn't keep every ID forever. I'd maintain a sliding window based on recent sequence numbers or time, removing old entries as they become irrelevant. If memory is extremely constrained, a Bloom filter could help, though it may create false positives. The design depends on packet rate and retention needs. In your answer, talk about hash sets for fast lookup, sliding windows for bounded memory, sequence ranges, false positives, stream size constraints, and time-space complexity. Question 20. Tell me about a time you found and fixed a difficult bug. I'd choose a bug where my debugging process is visible. In one project, an alert service occasionally missed events. I reproduced the issue with synthetic load, added time-stamped logs, and found a race between queue consumption and state updates. I fixed it by making state transitions atomic and added concurrency tests. The missed alerts stopped, and the team added a checklist for shared state changes. The key point was proving the cause, not guessing. Be sure to structure the story using situation, task, action, and result. Emphasize debugging discipline, evidence gathering, collaboration, root cause, measurable impact, and what you changed to prevent recurrence. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.